part of your body is doing something physically impossible right now. Electrons inside your cells are passing through solid energy barriers they don't have enough energy to cross. And it's not a glitch. It's one of the strangest, best confirmed effects in all of physics. In classical physics, if a ball doesn't have enough energy to roll over a hill, it simply rolls back down. It cannot end up on the other side. But a quantum particle, like an electron, doesn't behave like a solid ball. It behaves like a spread-out wave of probability, and that wave doesn't fully stop at the barrier. A small piece of it leaks through to the other side, meaning there's a real, measurable chance the particle simply appears past the barrier without ever having the energy to go over it. This isn't a new or fringe idea. In 1928, physicist George Gamow used quantum tunneling to explain something that had puzzled scientists for years: why unstable atomic nuclei undergo radioactive decay at all, releasing particles that, by classical physics, shouldn't have enough energy to escape the nucleus. Tunneling was the answer, and it matched the data precisely. It's been a cornerstone of nuclear physics ever since. Nowhere does tunneling matter more than inside the sun itself. At the temperature and pressure in the sun's core, protons simply don't have enough classical energy to overcome their mutual electromagnetic repulsion and fuse together. By the numbers alone, nuclear fusion shouldn't happen there at any meaningful rate. Quantum tunneling is what closes that gap, allowing a small fraction of protons to tunnel through the repulsive barrier and fuse anyway. Without it, the sun's core wouldn't sustain the fusion reactions that have kept it burning steadily for over 4.5 billion years. Here's where it gets personal. Many enzymes in your body, the proteins that speed up nearly every chemical reaction keeping you alive, rely on proton tunneling to work as fast as they do. Without it, some of these reactions would be far too slow to sustain life. Researchers are also actively studying whether tunneling protons within DNA's base pairs occasionally contribute to spontaneous genetic mutations. That specific idea is still being tested, not settled, but the tunneling happening inside your enzymes right now is not in question. Tunneling isn't just happening inside you. It's built into technology you use every day. The scanning tunneling microscope, invented in 1981, images individual atoms by measuring a tunneling current between a needle-thin tip and a surface. And the flash memory inside your phone, your laptop, your USB drives stores every photo and file by deliberately tunneling electrons through a thin, insulating barrier. You are almost certainly touching a device right now that depends on this effect to function. There's a genuinely unresolved question that comes with all of this. How long does tunneling actually take? Using ultra-fast attosecond laser pulses, physicists have tried to time the exact moment a particle enters a barrier versus when it exits. Some of these experiments have produced results that are still being debated, with some interpretations suggesting the tunneling process appears to take an oddly short amount of time. Physicists are still working out exactly what that means and whether it says anything meaningful about the particle's experience of time. It's an active area of research, not a settled answer. So why don't you ever see a coffee cup tunnel through a table? The probability of tunneling collapses exponentially as an object gets heavier and the barrier gets wider. For something as massive as a cup, the odds are so astronomically small that you could wait far longer than the age of the universe and never see it happen. Tunneling is real, constant, and measurable, but only at the scale of individual particles. Somewhere in your body, right now, a particle just did something that should be impossible, and it happens billions of times a second. Does knowing that change how solid the world around you feels? Let me know in the comments. New discovery.